Okay, so instead of doing this derivation in class tomorrow, I'm going to have you look at it tonight. So we can start tomorrow with problem solving on hyperbolas and a general kind of overall approach to problem solving with all three conics, regardless of what type of conic that we start with. So our last locus definition, and kind of given away by the terrible picture that's drawn with it, is a set of points for which the absolute value of the difference of the distances between two fixed points is constant. So whenever we pick a point, within our shape like this, I'm interested in the difference between the distances to the two fixed points. So I would take that D2 and that D1 that I've drawn and subtract them, and the claim is that this is some constant value. And that changes the shape. So we're going to dive right into the derivation. You'll see it's already pre-written, so you can just kind of quickly look at it. When the necessity of the algebra is not really so important. But you should look here at this shape that I've drawn and get an idea of the different parts. There are some additional parts to a hyperbola that we should pay attention to. We have the center, that's normal at 0, 0. We have the foci here and here, and those are at c units away from the center as we defined for the ellipse. We have the vertices, okay, those are here and here. Notice that this time the vertices fall closer to the center than the foci, so in this case we state that c is greater than a, right, and that changes some of our properties. The new portions for a hyperbola are called the central rectangle, and you can see I've drawn in this black rectangle on the screen, and the asymptotes, which run through the corners of the central rectangle. And they basically give the shape of the hyperbola. We know that a rotated hyperbola looks like a reciprocal function, so we should expect that a hyperbola that's simply on a normal set of axes has asymptotes of its own, and the key to finding those asymptotes are to think about the a and the b values and how they relate to one another. So in this case, there are no co-vertices for a hyperbola. We do have two axes. We call the main axis of the hyperbola the transverse axis. Okay, so the transverse axis is in the direction the hyperbola opens. And the other axis is called the conjugate axis. And that obviously is in the other direction. And we measure off a distance b, okay, on the conjugate axis, right, which for the ellipse was where the covertices fell. Basically, this b value is whatever the non-vertex distance is that's important to the shape. In this case, b, okay, is a value defined such that when I make a rectangle, okay, by going up b units and down b units from the center and over a units, right a units and left a units from the center. Notice how the asymptotes, those in yellow, right here and here, go right through the center. Okay, and that's how we define the central rectangle. It gives us an idea of the spacing of the hyperbola and helps us draw it. So from that point on, we start here with our written definition that d2 minus d1 is a constant. We replace the distances, and it will again turn out that the constant value is 2 times a, which is the same as the ellipse in the way that we started the derivation. And again, the reason for that comes from placing our arbitrary point, x, y, at one of the vertexes, okay, at one of the vertices, and looking at the total distance. You can do that on your own to confirm that that's true. I'm going to continue on through the proof. And you'll notice that this proof, which I'm not going to go through line by line, follows the pattern of the ellipse derivation very closely. You can see that I've squared one of the square roots away on this first line here. Then we collect terms together and then square again. And then go about isolating constants in x and y terms until ultimately we get down to x squared over a squared minus y squared over c squared minus a squared equals 1. Again, we want to make a replacement. And we want to make a replacement for c squared minus a squared because it's kind of ugly. In this case, we know that c squared is larger. In fact, the relationship changes under hyperbola. Notice that for a hyperbola I have over there on the left, that c squared equals a squared plus b squared. Another right triangle argument that we could make and demonstrate within the picture. That's different than for an ellipse. Within an ellipse, we have a squared equals c squared plus b squared. And the easy way to remember this is based upon the orientation of the vertices versus the foci. Which one is closer to the center? Right? If the vertices are closer to the center, as they are in the hyperbola, then a is going to be the smaller value. In this case, c is greater than a. If the vertices are farther away from the center, then a is going to be the greater value, like it is in the ellipse. So I can make the replacement then that c squared minus a squared is equal to b squared. And I'm left with x squared over a squared minus y squared over b squared equals 1. Nearly the ellipse formula, just a subtraction in the middle. It is not necessary that a be greater than b here. Okay? And in fact, it will happen about half the time a is greater than b, half the time a is less than b. Okay? The transverse axis is dictated by the leading variable, as you'll see here in the actual formula. So look, here we have the two formulas. The one where x minus h squared comes first is when the transverse axis is horizontal, and when y minus k squared comes first, the transverse axis is vertical. The important statement that a squared plus b squared equals c squared, and a does not have to be greater than b. Nothing says that is necessity. That's our basic form, right? We add those to it. We now have all the basic conic forms. These are the things we want to walk into class tomorrow comfortable with, in addition to a last set of properties. So let's go down one more. Right. We say, okay, here are some basic hyperbolas. And I'll write out the basic form. This is x minus h squared over a squared minus y minus k squared over b squared equals 1. And this would be y minus k squared over a squared minus x minus h squared over b squared, again, equal to 1. And we want to talk about things like the center, the vertices, the foci, and what we'd really like to know is the asymptotes. Because those are important to the shape of the overall graph. Center remains the same as it's been for everything, hk for both. The vertices, pretty simple to come up with. It's going to be h plus or minus a, comma k. For the horizontal one, we're going to have to move horizontally to get to those vertices. H comma k plus or minus a. For the vertical one, this shouldn't be super surprising to us given what we've seen so far about these general forms. Foci are h plus or minus c comma k and h comma k plus or minus c. The part that is new are these asymptotes, and the fact that we can find these asymptotes within the general form. Right? And we're going to find them within the general form simply thinking about the central rectangle that we might draw for a shape. So I'm going to draw the central rectangle in here. Right? And think about a line that goes through the corners of the central rectangle, like so. And if I want to find the equation of that line, I need to know its slope, and I need to know a point that's on that line. The easiest point to come up with that's on the line is the center, hk. And so if I'm thinking about point slope form, I want y minus y1 equals m times x minus x1. And I have a point. Those asymptotes always go through the center, hk. And the slope of those asymptotes is defined by that central rectangle, where we're going to go up b and over a. So the slope is b over a for the line that I've drawn here inside the picture. But there's two of them, right? And the other one is negative b over a. Right? I'm still going to go up the same amount, but I'm going to go left a instead. So the slope is really plus or minus b over a. So the asymptotes are of the form y minus k equals plus or minus b over a times x minus h. That's for the horizontal. For the vertical, it's a little bit different just because we have to still think about the box and how we calculate slopes. Even though we change the orientation of the hyperbola, we don't necessarily get to change the way that we calculate slopes. Because for this box, notice that we go up a and down a in that box, and we go left b and write b within the box. So when I go to draw the asymptote, the slope of this asymptote is a over b, as opposed to being b over a still. So when I want to write the asymptotes for a vertical, where the transverse axis is vertical, I write y minus k equals plus or minus a over b times x minus h. Alright? So you should look at these pieces, get the general idea of these pieces, and be ready to use them in class tomorrow. You won't be quizzed on them, and you don't have any homework problems on them tonight, but it is important that we have that information ready to go for class tomorrow.